Hi, this is Mrs. Vrobel. This is part 3 of Electrons and Atoms. This is the colorful section of the chapter. So we talked about what is light, how do we describe it. We talked about the wave and the particle properties. We talked about the photoelectric effect with Einstein and Planck's theory of light. Now we're going to look at why do we get color from certain elements. And I just want to share with you, I have this really cool looking ring. And the question is, where do we get all this color from the light that we see? Now, if you look at the spectra that I have there, so we have sodium, we have mercury, we have lithium, we have hydrogen. And notice that there's different types of colors associated with each element. And this is what makes elements special, is they have what we call bright line spectra. So sodium has one yellow line out of the whole series of possibilities. Notice that mercury, which is below it, it's got essentially 5 different yellow lines, and then it has 2 blue and then a handful of violet. There's a big difference between the two elements because the electrons actually determine what kind of light we see. So depending on how many electrons a specific element has, it's actually going to give us a certain color. And you're going to do a lab, or you have done a lab already, where you look at the color of the elements. And there's an overall color, and then there's individual colors. And what you see here is essentially individual colors for that specific element. Notice that there's a arrow at the bottom here. So on the right-hand side of the spectra, these are the shorter wavelengths of light. Notice that as you go to the left, like orange or red, we're talking about longer wavelength. So you may have done this lab, or you may not have done this lab yet. What essentially happens is we take a gas discharge tube. So we fill up a tube full of gas with a specific element. And it can't contain any air, because if it does, it's not going to give us the correct wavelengths of light that we're looking for. There's essentially 2 slits, and the slits help to modify the type of light that's coming through. You need a prism, because the prism is going to bend the light depending on what wavelength of light we're talking about. And notice that we have violet light all the way down to red. And the NM stands for nanometers. So we're talking about very tiny wavelengths of light. So what happens is these specific elements, they have unique energies. Not every element has the same type of light. So this is the nice thing about elements, is we can actually get specific types of light coming from that element. And you have to have an electric charge. This won't work at a steady state. So what's happening is the electrons that are within that element are being probed, or I don't want to say stirred, but they're essentially being electrified and disturbed. And when they do, they give off a certain color of light, and we're going to talk about how you get that color of light. But with the bright line spectrum that I just showed you, there has to be discrete energy levels. Otherwise, we would see a rainbow of color, and we do not see a rainbow of color. If we saw a rainbow of color, that would tell us that the electrons do not occupy, if we saw a rainbow of color, that means the electrons occupy many different places within the atom. But we know that is not the case, because we don't see that in bright line spectrum. Okay, now what's happening in the discharge tube? So before we see the color, what essentially is happening is the electrons are in their lowest energy state. So remember how we had the Bohr model of the atom? We saw the outer orbits from outside the nucleus. we know that the electrons occupy space outside the nucleus. And when we do not see color, we know that these electrons are in their lowest energy state. And the lowest energy state typically is called the ground state. So whenever you hear the ground state, that means the electrons are in their lowest energy level. When we see the color, so you know how I showed you that ring that was giving off those different bright lights, we have to have some kind of instability. So what's happening is the electric charge is coming in contact with these electrons, or you could have other electrons, so you could have bombarding electrons, forcing other electrons to higher energy levels. So think of it like ladder. You have the lowest rung of the ladder, which is called your ground state. You electrify these electrons. They move up to a higher rung of the ladder, and they go into higher energy levels. And this is what we call the excited state. So we go from the ground state to the excited state. Now, it takes a lot of energy to go from the ground state to the excited state, and that's why it's unstable. When we see that color, we have to have a release of energy. So we see the color when those electrons return to their lower energy or the lower rung of the ladder. So as they're returning to the lower energy state, we see that color. And that color that we see actually uses up a certain amount of energy. And that's why we get different colors, is because the different colors use different levels of energy. I love this slide because in this slide, it actually gives you a really good representation of what's going on when we see the different colors from elements being excited with electricity or other electrons. So here we have three different colors. We have red, blue, and, red, green, and blue. You may notice that the way these colors are drawn, there's a different frequency to each type. So if you had to guess, which one has the highest frequency? Yes, hopefully you said blue. So notice that there's more squiggly lines with blue, therefore it's a higher frequency. Now, if frequency is high, so if nu is increased, what do you think happens to energy? Energy is increased. So on red, if you have a lower frequency, energy is going to be lower. And obviously, the green color is somewhere in between. Also, when you look at the energy levels, 3 to 2 to 1, this is actually not drawn to scale, unfortunately. There's actually a wider gap between 1 and 2 than there is between 3 and 2. They kind of drew it evenly spaced, but ideally the gap between 2 and 1 is big. So the energy level difference between 1 and 2 is much bigger than the energy level between 2 and 3. But anyways, notice that when you go from energy level 3 down to 1, this has the greatest energy level difference. Hence the reason why we see a blue color is it's a larger energy requirement than going from 3 to 2. Now, what does this mean? There's actually 3 series, and you will get to know these very well. There's what we call the Lymann series. Notice that the Lymann series is in ultraviolet. Can you see ultraviolet? No. However, I will tell you, I did come across one person who had cataract surgery, and she actually found, because of her cataract surgery, because they did something to the lens of her eye, she can actually see a little bit of ultraviolet. And that's very unusual. Not all humans can do that, but she did because of her cataract surgery. Notice that we typically see the visible light. So the Balmer series is something we can see with the naked eye. We don't need another instrument to tell us that we're seeing those colors, okay? However, the Paschen is infrared. What I would do is maybe make some flashcards for yourself, because you will have to know the difference between Lymann, Balmer, and Paschen, just to let you know. And notice as you go from ultraviolet to infrared, the energy decreases. if you go from ultraviolet to infrared, the wavelength increases, and then lastly, the frequency will decrease. Now notice that the bright line spectrum is only for hydrogen. Okay, so the Paschen, Lymann, and Balmer series only works for hydrogen. It's different for other elements. Okay, this is a representation of the lines for each series. These are energy levels. So for each series, we're talking about a different set of energy levels. So notice that at the top line, this is actually infinity. Okay, so the very top line is infinity. All of these energy levels eventually reach infinity. The closer you get to infinity, the more narrow the difference between the energy levels. So notice that, like I was telling you, that picture that you saw 2 slides ago, there's a big difference between the first and second energy levels. Okay, it's biggest compared to the other series of energy levels. So the Lymann series, we're talking about going from an electron dropping down from 2 to 1 all the way up to infinity. And then with the Balmer series, remember we can see the Balmer series, we can't see the Lymann or the Paschen. We're talking about energy level 3 down only to energy level 2, okay? So the first color of light that we see in the Balmer series is going from energy level 3 down to 2, and this is only in hydrogen. So all 3 series, we're only talking about hydrogen element. We can talk about energy level 4 to 2 and so on all the way up to infinity. And then lastly is the Paschen series. So we're talking about infrared. And we start with energy level 5 down to 3, and so on, all the way up to infinity. So like I said, you will need to know the difference between Lymann, Balmer's, and Paschen. Remember, Lymann is ultraviolet, Balmer is visible, and Paschen is infrared. Lymann, we're talking about the first energy level going from 2 to energy level 1, all the way up to infinity. Balmer, we're going from energy level 3 down to only energy level 2, all the way up to infinity. And then Paschen, we're talking about energy level 4 down to energy level 3, all the way up to infinity.